filter design, and frequency extraction in Python. I'm working on a project to find the instantaneous frequency of a multi-component audio signal in Python. I am currently using a Butterworth bandpass filter combined with scipy.signal.filter to extract around my desired frequency region. I then use the analytic signal from scipy.signal.hilbert to get the instantaneous phase, which can be unwrapped to give frequency. As a relative novice to signal processing, I have two main questions. I have read that in many applications, it is preferable to use scipy.signal.filtfilter over scipy.signal.willfilter. Certainly when I apply filtfilter to my data, I get a significantly smoother looking instantaneous frequency signal. I would like to know the major differences between the two, bearing in mind that I would like to get an output, which is as close to the true, instantaneous frequency as possible. The instantaneous frequency data is non-stationary, which means that in some instances I must use a wider bandpass filter to capture all my desired data. This appears to introduce additional noise and occasional instabilities into my signal. Are there ways to deal with these kinds of problems, for example with a better designed filter? Edit. In response to Flebel, below are some images of the data I am looking at. First, a comparison of filt and filtfilt. Both the above signals have had the same Butterworth filter applied, although the filter function is different, followed by extraction of instantaneous frequency, which is what is plotted as a function of time. Filtfilt seems to shift and smooth the data. Is one of these signals a better approximation of the true signal? Note that this graph shows just a subset of a particular signal. Second, the effect of increasing the Butterworth filter size. This is for the same subset of data as Figure 1. The legend shows the lower and upper bound for the filter. Respectively, the red trace is the filt version of the data in Figure 1. Although it may not be clear here why I would use a larger passband, in some instances the data may be located at various points between, say, 600 and 800 Hz. It is here that I would require a broader filter design. You can see that additional noise enters the trace as the filter gets wider. I like to know if there's a way to optimize/improve my filter design.
To your first problem I can't speak intelligently on, but scipy is generally well documented, so I'd start reading through some of their stuff. To your second problem, a better designed filter would certainly help. You say the data is non-stationary. Do you know where it will be? Or what kind of frequencies it might occupy? For example, if the signal is centered around one of three frequencies that you know a priori, you could have three different filters and run the signal through all three, only one giving you the output you want, of course. If you don't have that kind of knowledge about the signal, I would first do a wider BPF, then do some peak detection, and apply a more stringent BPF when you know where the data you would like is located.
Some sparse comments. 1. On the top picture, I can't comment on what is best between filt and filtfilt, though the shift in frequency of filtfilt is worrying. You can obtain a similar result by applying a low-pass filter to the filt signal. 2. There isn't a true instantaneous frequency unless the signal was specifically generated with a certain tone. In my experience, unwrapping the phase of the Hilbert transform does a good job in many cases, though. It becomes less and less reliable as the ratio of noise to signal intensity grows. 3. Regarding the bottom picture, you say that sometimes you need a large bandpass filter. Is this because the signal is very long and the instantaneous frequency moves around between 500 and 800 Hz? If so, you may want to proceed windowing the signal to a length at which the filtered signal has a distinct peak in the Fourier spectrum, extract that peak, tailor your band-based filter to that peak, apply Hilbert to the windowed signal, extract the phase, filter the phase. This is worth doing if you are sure the signal has other harmonics except noise and the one you are interested in, and it takes a while. Before doing so, I would want to be sure the data I obtain is wrong. If it is simply one harmonic plus noise, I would low pass plus Hilbert plus extract instantaneous phase plus low pass again on the instantaneous phase.
If you want to support the channel, please consider liking and subscribing.